What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about the acid ionization constant, what it is, and how to actually find it in a problem. So to first start off, let's actually define what the acid ionization constant is, and what you're going to see is a reaction with just some sort of acid, and this is going to mainly be a weak acid, and you'll see why this is a weak acid. It's because if you see these double bars, it means we are in equilibrium. We're in dynamic equilibrium, and this indicates a weak acid. The reason why this is a weak acid is because it doesn't ionize fully. If it did ionize fully, then we'd only see one full arrow going from the reactant side to the product side, showing that all of the reactants have basically ionized. This whole acid has ionized, and that's what results in this strong acid. But in this case, for acid ionization constants, we have a weak acid because we have this equilibrium sort of double arrows, which indicates that we have a weak acid. Same thing for bases, which we'll also talk about. So we have a weak acid over here, we have water, and that goes to hydronium, so H3O plus, and our conjugate base. So this is our conjugate base over here. This is our weak acid, so I'm just going to sort of label these. So this is our weak acid over here. This is obviously water. One thing to note though is that water will always be in a liquid state. And that's the physical state for water. So the weak acid and let's say the hydronium as well, those will mainly be in aqueous form, and water will be in this liquid form. Now the reason why that matters is we'll actually talk about that very soon. So here's our hydronium, and this is our conjugate base. So that's our conjugate base. Now like I said, this physical state of water really matters because our acid ionization constant, which is labeled as Ka, or it's shown as Ka. Let me actually write that a little bit better. Ka. This is pretty much kind of similar to reaction quotient where we had those products over reactants. So same thing over here. It's going to be the concentration of hydronium times our conjugate base over our acid. The reason why we don't put water is because water is in the liquid state while everything else is in the aqueous state. And remember when we were talking about reaction quotients in our equilibrium unit, where if we had something that wasn't in aqueous form like solid or liquid, then we don't really qualify that in the reaction quotient. Same thing over here. We don't qualify water because it's in a liquid state. And see over here, this pretty much is similar to the reaction quotient where we had our products over reactants. Now another way of writing this Ka, which pretty much it's going to be the same thing, but you could also have your hydrogen concentration and your conjugate base. So here's another way of writing that Ka where you have your hydrogen concentration times the conjugate base over the weak acid. Okay, so now that we know that, let's go through a practice problem. I'm just going to leave these two up above. So our sort of problem is we're given hydrofluoric acid, and obviously there's water, and I'm not going to be labeling the physical states, but just remember hydrofluoric acid, everything else will be in aqueous form, water will be in a liquid form. So we put the double bars because hydrofluoric acid is a weak acid. And remember, if you want to recall how to remember your strong acids, it's so I brought no clothes, and then you also remember that it's HCl3 and HCl4. So those are the ones you have to memorize, and if those strong acids are not present in the solution, then you just automatically assume that it's a weak acid. So hydrofluoric acid is not part of the strong acids. So I brought no clothes. There's no F in that acronym. So that means that hydrofluoric acid is a weak acid. That's why I put the double bars, and that's why we're going to find our acid ionization constant. So I put those double bars, and we're going to have hydronium and fluorine. So just as a sort of a review, pause this video and see if you can find which one is the conjugate acid or the conjugate base. So if you guessed that fluorine was your conjugate base, you're definitely right, because hydrofluoric acid is your weak acid. The reason why it is an acid is because it is donating a hydrogen, and acids are the ones that, according to the Bronsted-Lowry acid base theory, the hydrofluoric acid will be the Bronsted-Lowry acid because it is donating a hydrogen, and this would be our conjugate base. So that's sort of a refresher, and one of the questions we are asked is, and let me actually move this over here to write down what we need to find. So it's asking us to find the pH if we have 0.50 molars of hydrofluoric acid. So, and this is assuming that we're in 25 degrees Celsius. So it's going to tell you the standard temperature, which is 25 degrees Celsius. So we don't really have to worry about temperature. And finding the pH. So it's asking us finding the pH if we're given an initial of 0.5 molars of hydrofluoric acid. So automatically what we can do is set up a Rice table because this is in equilibrium. We need to find the change in our hydrogens in order to sort of understand what our pH is. Now, to do that, we need to know our Ka. And you might be wondering, well, why didn't they give us a Ka? Well, they more than likely, if you're taking a multiple choice practice exam, they will give you the Ka because they won't give you, or I really don't know how your professor creates your exams, but I believe they wouldn't give you an entire formula sheet of just all the Kas paired up to different reactions because that just takes time for them, takes time for you. So it seems counterintuitive to do that. So they're more than likely give you the Ka, but there is a sort of formula sheet or a cheat sheet to look at for different reactions and what their Ka is. And in this example, our Ka for this sort of reaction is 6.8 times 10 to the negative 4, and that equals our Ka. So now that we know that as some background information, we can go with our ice table or Rice table. So remember, if you don't remember how these kind of work, R stands for the reaction, I stands for initial, and initial we have 0.5 molars. We can forget about water because it's in its liquid state, and that does not count in the acid ionization constant, so we can forget about that. For hydronium, we have a 0 initial, and fluorine, we have a 0 initial because we're not given those initials, so we can just assume that they're 0. Now, the change is more than likely going to be negative minus x over here and x over here. The reason why is because whatever the change is, it needs to be positive for this hydronium and this fluorine, but we can subtract it from that 0.5. And also, because this change in over here, this hydrofluoric acid is going to be our products. So in equilibrium, when we're going from left to right, we are decreasing in the amount of reactants we have, we're increasing the amount of products we have until we get into a point where the rate of the forward reaction equals the rate of the reverse reaction. Now, this doesn't mean that both concentrations are the same. If we remember from our past equilibrium unit, equilibrium doesn't mean both the reactant and product concentration are the same. That is not what it means. It means that the rate of the forward reaction equals the rate of the reverse reaction. So more than likely, we're going to be increasing the amount of products and decreasing the amount of reactants. So this is why this is 0.5 minus x, and over here we just have x and x. So if we remember from our Ka, it's hydronium times our conjugate base over our acid. What's our hydronium? Our hydronium is x. Our conjugate base is x as well. So this is times x. And this is 0.5 minus x. And that equals our Ka, which equals 6.8 times 10 to the negative 4. So now that we know that, we can actually change this to x squared because both of those values will be the same. So we can make this x squared. And here's one rule you have to know, which is the 5% rule. So this 5% rule allows us to make this change in 0.5 negligible. So what is the 5% rule? Well, to find the 5% rule, it's basically stating that the percent of ionization can't be more than 5%. And if it is more than 5%, we can't neglect the change. So what this basically means is if it's less than 5%, the percent ionization is less than 5%, then we could take out this x, because whatever that change in, it will barely even move this 0.5. So to find that, we first want to assume that we can just make x negligible. So it would be x squared over 0.5. And this is actually how you check if this is less than 5% and you can make that x negligible. So first you just forget about the x, you forget about this change in the bottom, and you make that equal our Ka, 6.8 times 10 to the negative 4. Obviously you do basic algebra, 0.5 times 0.5, and what you should get is, let's see, we do 6.8 times 10 to the negative 4 times 0.5. So and I'll move over here, x squared equals 3.4 times 10 to the negative 4. Square root that, and we'd get x equals 1.8 times 10 to the negative 2. And I just rounded there because it is 0.0184390 or whatever, but I just rounded to 2 decimal points. So let me actually move this a little over here. So that is our x right there. And our x represents our hydronium concentration and fluorine concentration. Now, we still have to check if this is less than 5%. So how do we do that? Well, we get our change in and we divide it by our initial amount of hydrofluoric acid. So this would be 0.8 over 0.5. So that divided by 0.5. And we have to multiply by 100 to get a percentage. So times 100. And that is equal to 3.7%. 3.7 is less than 5, so we can assume that the change in x is negligible. So that's how you find out if you can pretty much eliminate this x over here and just assume it's 0.5. So now that we know that, we can just erase all this math because we already know our percent. So our percent doesn't really help us in finding the pH. It just helps us, allow us to basically eliminate that change in and make it negligible. So now that we have that, this x equals our hydronium concentration. Now, if we remember, pH equals negative log of our hydronium concentration, or it could equal negative log of our hydrogen concentration. But since we have hydronium, our pH equals negative log of 1.8 times 10 to the negative 2. And that would get us, let's see, negative log of 1.8 times 10 to the negative 2. That will get us 1.74 as our pH. So that is exactly how you find your pH given your mores and your Ka. And if you want to double check this, you could actually do, let's see, since our x is 1.8 times 10 to the negative 2, that would be 1.8 times 10 to the negative 2 squared, because over here we said our x is 1.8 times 10 to the negative 2. So if we plug in x, it's just x squared, so 1.8 times 10 to the negative 2 squared. And over here, this would be 0.5 minus 1.8 times 10 to the negative 2. Let's see what that gets us. And that gets us 6.7 times 10 to the negative 4, which is pretty close to 6.8. So we just had some rounding errors, but pretty much the same sort of idea. And If you're given a multiple choice question, more than likely you won't be given like 1.745 or 1.746, that close of a number. So this is exactly how you find your pH. Now over here you could have put 1.8089 or whatever the other numbers were, but I just rounded up to 1.8 just to make it clean and just to sort of go through this problem much easier. So that's exactly how you find pH, giving your molarity and your Ka. And here's one tip you should actually really keep in mind, is that if the percent ionization is less or is greater than 5%, you use the quadratic formula. I'm just going to say quad formula. And the reason why is because if it's over 5%, you can't assume that this change in X is negligible. So you have to go through all the quadratic formula, multiplying this over here, then moving on the other side. It just becomes sort of a big hassle. So really try to find your percent ionization first before you actually find your X. If it's greater than 5%, then you got to go back and use the quadratic formula. But if it's less than 5%, well then everything's pretty much easier from there. Now let's move on to the base ionization constant. Same thing, pretty much the same thing here, where this only applies to weak bases. And we'd have something like our base plus water. Water is in our liquid form, so I'll just put liquid right there. We have our double bars showing equilibrium because this is a weak base. And we have our conjugate acid. So this is a conjugate acid, and the reason why is because it pretty much, like when you have a base, you have a conjugate acid like we talked about in previous units. And the reason why this is a base is because in the product side it accepted a hydrogen, so that's why it's a base. And we have OH instead of hydronium or hydrogens. So same thing over here, same concept, but our base ionization concentration will be denoted as Kb. So it's pretty easy to identify Ka versus Kb. That Ka is for acids, Kb is for bases. So this is just products over reactants. So this is going to be our conjugate acid times our hydroxide concentration over our concentration of our base. So that is Kb right there. It's very similar to Ka, but we're just dealing with bases. That's pretty much the only difference. So I'm going to leave this up here and let's go through a practice problem real quick. So it asks us, what is the pH of 0.040 molars of, and I'll put, let me do NH3 or ammonia, and then in 25 degrees Celsius because this is standard temperature. So what is the pH of 0.04 molars of ammonia? Well, the reaction for that would be NH3 plus H2O, and we have those double bars, and that goes to ammonium, so NH4 plus, and plus hydroxide. And for this question, usually you're going to be giving your Ka, but just as reference, or Kb, my bad. But just as a reference back here, our Kb is going to be 1.8 times 10 to the negative 5. So this is pretty much the exact same method for finding the pH for our acid, where we're just setting up our rice table, so reaction, initial, change, equilibrium. So our initial for our ammonia is given, which is 0.04. Water, we can just forget about it since it's this liquid state. And our ammonium is 0. Hydroxide is 0 for initial concentration. Now our change in is going to be minus X plus X plus X. We don't know what X is. We don't know our change. And this is going to be 0.04 minus X. This is going to be X, this is going to be X, so this is just going to be X squared over 0.04 minus X equals 1.8 times 10 to the negative 5. So, like we talked about with our first step, the first step is to find the percent ionization because we need to know that in order to make this change, assume this change is negligible. So what we do is we just automatically assume at first that the change is negligible. So this 0.04 equals 1.8 times 10 to the negative 5. And I'm just going to do the speed through the math real quick. So this is going to be 0.04 and square root that. So this is going to be 2.12%. And if you go through the whole math, that's, I pretty much believe that's what you get, or 2.13%, somewhere in those lines, but obviously it's going to be less than 5, so we can assume that this change is negligible. So now we just go about our problem, but we already found our x if you solved it, but I'll just pretty much solve it again. So let me move this to this side over here. And this is going to be x squared equals 0.04 times 1.8 times 10 to the negative 5. And let's see what that gets us. 0.04 times 1.8 times 10 to the negative 5. So that gets us x squared equals 7.2 times 10 to the negative 7. And if you square root that, then our x is going to be 8.5 times 10 to the negative 4. So now that we know our x, this x represents our hydroxide concentration, also our ammonium concentration, but we need this hydroxide concentration because if we remember, POH equals negative log of OH minus, or the hydroxide concentration. So since we have our hydroxide concentration, we can find our POH. So this is going to be negative log of 8.5 times 10 to the negative 4, and that equals our POH. And let me scroll down over here for some more room. So if we do that, that will be negative log of 8.5 times 10 to the negative 4, and our POH is going to be equal to 3.07. But we're not done because that's POH. That's not pH. If we remember, pH plus POH equals 14. They will always add up to 14. So if we know our POH, we're trying to find our pH, we just move this POH over. So this is going to be pH equals 14 minus 3.07, and that equals 10.93, and that is our pH. So one of the things that sort of gets me as well is when I find my POH, I kind of assume that's my pH, because first off, usually I don't really write POH equals, I just do negative log of whatever the concentration is, and then I think that's my pH. But you really have to remember the difference between POH and pH, because once you find your POH, you can use that to find your pH, and that's what you really need to find. So there's a reason why this is 10.93. Not only that we have our POH and we're sort of converting that, but also this POH concentration is pretty high, because if we remember Ka times Kb equals Kw, Kw equals 1.0 times 10 to the negative 14. So this is going to be actually let me change this. I believe it's going to be, I think it's something like Ka times Kb equals Kw. But one of the things you need to notice is that if this concentration, 8.5 times 10 to the negative 4, is pretty high, and then this concentration is actually pretty high, then we're going to have a base. We're going to have a basic solution. Now remember, there is some sort of cheat sheet, or there is a reference to help you understand if the concentration is bigger than this, then it's going to be basic. If it's smaller than this, it's going to be acid. So something like that. I'm pretty sure there's like some image over there, but one of the ways I just sort of solve this is just do negative log, because I always forget which numbers indicate that it's a basic solution, which one is a acidic solution. But I'm sure there is some sort of number out there, some sort of, I guess you could say, standard, where if it pretty much is larger than this, it's basic. If it's lower, then it's acidic. But that is how you find pH given your concentration of hydrox, or trying to find your concentration of hydroxide. And it's just an extra step compared to our previous practice problem. So let's do another practice problem, but now let's try to find Kb given our pH. So this is going to be a little bit different, but still the same steps. So let's say we have 0.15 molars of caffeine, which has a pH of, now let's just say pH of 8.45, and we're asking what is the KB. We're wanting to know what our KB is. So if we do this chemical formula, we draw out this chemical formula, and on a practice exam, they are going to give you your chemical formula if it's something like caffeine, because obviously you don't really have to memorize the chemical formula, the equation for caffeine. So this is going to be C8H10N4O2 plus H2O. And we have those double arrows per usual, and then we have C, and then we have H because this is a base, so it's accepting a hydrogen. This is a Bronsted-Lowry base, so it's accepting a hydrogen. So this is C8H10N4O2 plus, because we just got a hydrogen, and plus our hydroxide. So first thing we want to find is our pOH, because we're dealing with bases. The only way to find our Kb is to find our concentration of hydroxide, which is our X, and the only way to find X is to find our pOH. So remember that pOH equals 14 minus pH. If we know that, then 14 minus 8.45 is going to equal our pOH, so 14 minus 8.45, that gets us 5.55. And another equation to know is that the hydroxide concentration equals 10 to the negative pOH, so this is going to equal 10 to the negative 5.55, so 10 to the power of negative 5.55, and that gets us 2.82 times 10 to the negative 6 molars, and this is our change. So I'm going to highlight this just to emphasize the fact that this is our change. This is our change in X. This is our concentration of hydroxide. This is the concentration of our conjugate acid. This is our X. So let's open up that rice table, and R stands for our reaction initial, change in equilibrium. So our initial for our caffeine was 0.15 molars. We can forget about water because it's in its liquid state. Over here, our conjugate acid was 0, and our hydroxide concentration was 0. So our change in, which we know, was 2.82 times 10 to the negative 2. Over here, 2.82 times 10 to the negative 2, or my bad, negative 6. This is going to be negative 6 over here. So 2.82 times 10 to the negative 6. 2.82 times 10 to the negative 6. So yeah, that's our X over here. So then this is going to just be 0.15, because when we did that percent ionization, it was 2.8 times 10 to the negative 6 over 0.15 times 100. And that gave us something less than 5%. That percent ionization was less than 5%, so we could just pretty much forget about the X, and our equilibrium would just be 0.15. Over here, our equilibrium is 2.8 times 10 to the negative 6, and 2.8 times 10 to the negative 6. So all we have to do is this squared over 0.15, and that's how we got our KB, which was 5.3 times 10 to the 5.3 times 10 to the negative 11. So negative 11th power. So same thing over here where we got 5.3 times 10 to the negative 11. And that is pretty much how you find your KB given your pH. And this is the same exact process you use for finding your Ka given your pH. But that one's a little bit much easier because your pH, all you have to do over here, we had an extra step because we had to find our pOH. But if you were given your pH and you're trying to find Ka, all you really have to do is just 10 to the negative pH, and that gets your concentration of hydronium or hydroxide. Just keep going through this sort of process. But another point I really want to emphasize is find your percent ionization. Your percent ionization is your change in over your initial concentration times 100. If it's less than 5%, then you can say, or you can assume that that change in, that X is negligible. But if it's not, then you have to use quadratic formula because that change in X is not negligible. So hopefully you learned something about the acid ionization constant and the base ionization constant. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.